Okay, today is a paper day. I started reading this paper just today, actually. And I guess it's not strictly a paper day. It's based off of starting reading this paper, but I'm actually not going to go into the manifold constraint part. I'm literally like 2 pages into this paper. But as of this reading, I am just now learning about hyperconnections. So I'm going to go into hyperconnections. Okay, so typically you've got the standard transformer architecture where you do, at least through the Karpathy series, you have X, and you continually add on to it, and that's called a residual stream, and that's supposed to help with the gradient, with a gradient problem, all that kind of stuff. Which, let me pull up an example of basically where that is. Let's see, so use the blocks. It is tension. Where is this at that I'm looking for? Right here. So, inside the block, what you do is you take your input and you do the self-attention on it and add it back to the input to get the next piece. And you do that again with the feed forward layer. You transform this using the MLPs, multi-layer perceptrons, and you add it back to the original. And you do that in each block. So you just can keep doing that through each block. And that's the residual streams, is each of these that you're just adding on to the original input to make the changes. And then, so that's this diagram here. And then hyperconnections, we're not gonna go into this over here, but with hyperconnections, basically, you'll start with your input X. It's gonna have an embedding dimension, let's say 64. And what hyperconnections do is it splits that 64 into two pieces, into two different parts. There's the expansion part, and there is the, what did they call it? The N and C. N is the expansion, and C was the base width. So that way they could break it out into different parts. So you have, let's say, 64 embedding dimensions. You break that into expansion and base width. So let's say your expansion rate number is 4. So you do 64, break it into 4 parts, and you'll break it into 4 tensors of what is that, 16? Of 16 width. So your new embedding dimension for each of these, it would be 16. And so that goes through this residual, it's a residual mapping, and then you also have the residual stream come over here still, but it's a different infrastructure, we'll go through the code here. Okay, we'll start at the highest level and work our way in. So we'll start at this new transformer block. Everything else is going to be the same if you use the Carpathy transformer. Still basically the same. I got rid of the head block, the head class, and the from the head to the block, because we're replacing the block and everything from block down, which is so this one's not explicitly based off the original Carpathy video. I added in from his tokenizer video, added in byte pair encoding for this one here, but you can still use everything I'm talking about for the original, or maybe I'm sure the byte pair encoding is in his GPT-2 video as well. But I got rid of everything: block, feed forward, multi-head attention, and head. So from head down to block. And replaced it with this transformer block is the bottom, all the way up to hyperconnection wrapper, which we'll go through. Okay, so let's start with the transformer block. That is used to replace this block. You take, so yeah, we'll start here actually. So transformer block, the hyperconnection transformer block. Instead of an number of embeddings, you'll do an embed divided by expansion rate, which I set to 4 up top here. Made an expansion rate of 4. And so we put in, so this will be the base. Right here is the base width, and then the expansion rate. So you have number of embeddings, you're going to break that into expansion rate, which is 4. You're going to break it into 4 pieces of base width. And then you still need the number of heads. Okay, so that goes into this transformer or hyperconnection block. And what you do is, so you'll set C as the base width, N as the expansion rate. You'll have a normal self-attention here, which is actually multi-head attention, which will go into this class. You set that as the attention core, and then you have the hyperconnection wrapper, which you will put this attention core into. This hyperconnection wrapper takes that base width, C, that expansion rate, N. So you could do self.c, self.n for these as well. The layer inside is the attention core here. You create an MLP. So it's pretty similar. You're going to use the attention and then the MLP in the standard transformer. And then, yeah, so you'll have one for the attention, one for the MLP, and you'll do the attention on it, and then the MLP on it. Okay, so now let's go ahead and go into this connection wrapper. I guess real quick we can go into the self-attention and hyperconnection. The self-attention and the MLP, just so you see what the one looks like that I'm using. I got all this code from Gemini. I mostly understood it, but I honestly didn't quite understand how they were getting the expansion rate and base rate at first. So I just threw it in there and was like, oh yeah, they're just breaking it out of the embedding dimension. Cool. So first got the MLP, which is a layer norm, and then a sequential of a dense layer. I don't actually know how you say that. Maybe GLU, which is it's like ReLU, but it's, as far as I understand, it uses a Gaussian in there. Let's see real quick. GLU function. I have not used it. I've read about it. Gaussian error linear unit. Okay, so smooths ReLU by weighting inputs by their probability under a Gaussian. Interesting. Looks like this. Using a cumulative distribution function. X times phi is CDF. Okay, gotcha. So basically, in a cumulative distribution function, it starts at 0 from over here and goes up to 1. So it's the CDF of the Gaussian, which is a standard normal. So standard normal would look like the bell, but the cumulative would, like I said, start from 0. It adds up the pieces of the Gaussian, of the standard normal. So it goes from 0 to 1. So this goes from 0, it would be at the far end on the left, it would be 0 for this Gaussian part times the x value. And then as you go further out to the right, it will do so it gets more negative here because, so it's this blue line, gets more negative here because you're getting a higher cumulative probability. So this gets non-zero and you're multiplying with a negative x, with a negative value. So it is negative, and then you hit 0. So whatever the distribution number is times a 0 value will still be a 0. And then, so this is probably 0.5 would be the, yeah, because 50% would be less than the mean. So that'd be 0.5 times your x value, which would be 0. And then that will go up then the rest of the values are positive. So greater than 0.5 times whatever your positive x value is. And then as you go up here further, you get closer to your CDF being close to 1 times the x value. So basically, it is the x value. So yeah, as you get closer up here, it gets closer to the ReLU, which I find to be much better than ReLU. But yeah, okay, so there's that. Where was I going with that? Okay, so dense layer, GLU, another dense layer. If anybody knows how to say that word, let me know. So you have that, causal self-attention. They just have, using Gemini, I just used this. Could have separated or used the attention that we had created in the Karpatha videos. Didn't think it really matters that much. So you have the layer norm, multi-head attention. So doing the forward, you'll have the norm, self dot layer norm. Your attention will be I actually don't know the inputs you need here. Let's see here. Yeah, I'm not actually sure of their inputs of like NN's actual multi-head attention. Oh yeah, it looks like they don't have the attention mask. Interesting. So that would have to be added in. I just, like I said, use Gemini real fast to get an understanding of what's going on here. So you have the attention mask, the MLP, and then you have this wrapper, the hyperconnection wrapper, which gets used with the base layer of the attention core and with the base layer of the MLP. So we'll assume base layer of attention core in going through this. So you need the base width, which we said was 16. Expansion rate is 4. Put those together, it'd be 64, which I typically have as the embedding dimension. Sublayer would be the attention. Self.c, and put those values in. Okay, so we have HRes, which is the HRes is residual stream. Let's see, this HRes. So I guess it's a residual mapping which goes on rather than just having the input x values themselves. You map that right here, and then you're also going to do this here. So let's see how this code goes through that. Okay, so first HRes, this will be a tensor that puts it into parameters. So basically a layer that can have gradients and all that. Torch.I of the expansion rate plus torch.rand of self.in by self.in. So This is a 4x4, which this is also a 4x4. I can show you, I did a little test to see what that looks like. Let's see here. We'll just restart. Torch the tensor. So this residual is what we're trying to print. So it creates this if you add them together. The torch.I is zeros on the or off the diagonal. So this is the diagonal. Oops, sorry. This is the diagonal. Off the diagonal, torch.I makes 0. Off on this side also 0, but it's 1 for each of these. And then just adds in some random noise, and this basically keeps the input close to being the same. Starts it off close to the same as itself. It has this pre, which is torch.rand_in. This pre is, let's see, the pre is this right here. So it has the normal one, it has the pre, which is going to go into this. This here was breaking out the input. All of this here breaking out the input into its 4 channels. So if we go back here, I was using this batch of 2, sample of 3, which I could just make that 1, keep it small. Yeah, save, and we'll do this. Okay, there. So we got a batch of 2. So 1, 2. The sequence length is S of 1. So 1 sequence. N of 4. Or let's see. Okay, yeah. So sequence of 1 is not just this, but it's 1. There's just 1. N of 4. So N by C would be the together would be the test embedding dimension. So let's say, so here it'd be like an embedding dimension of 20. 4 times 5. You break it out into 4 sets of 5. So 1, 2, 3, 4 of 1, 2, 3, 4, 5. So that's how that's broken out. Your input's broken out into that. And then this residual acts on each of these 4 sets. Okay, so yeah, so this one, like it says, mixes the streams. Yeah. This one will compress, and we'll see that in the forward. And then post will, so we compressed here, we gotta decompress here. So then the forward function, you get the shape, the batch sequence, and then the N by C. We reshape it to batch sequence N and C, breaking out that embedding dimension. We'll use einsum, which is Einstein summation. If you don't know much about that, it's cool. It's used for higher level tensors, Could definitely look into it. If you want to learn general relativity, you need this. So residual branch is going to take the BSNC n times m, which really is n by n, which is the, see, it takes the h residual, which is this one here that we did, the ones on the diagonal, and a little bit of random noise. So yeah, take the input, multiply it by that to mix things together. And so x reshaped BSNC times that residual, mix things together. The layer input is shrunk down to the B batch sequence, and C, which is the base size, which we were saying was 16. Yeah, so that's the input, the output gets that, takes the input, does the self.sub layer, which is the attention. This is where you do the attention. Or when we do the MLP part, this is where you would put the MLP on it. And then you do the Einstein summation to get back out the output, because you have shrank it. Now you have to unshrink it with the hpost. So hpre was a 1 by n to shrink it down. Hpost is a 1 by n to expand it back out. And then you return the residual branch. This is where it's more like this part. So we did the residual mapping here, the pre, the attention, and the post is over here in that stream. And then you add them together to add them together right here to go into the next layer. So that's that. Yeah, and so that gets you this whole hyperconnection thing. I've got more to read into it, because now I still don't know really anything about this manifold constrained hyperconnections, which is this whole part. If I figure it out and can code it up, I will let you know. The other thing you would need to do is put in a causal mask. Otherwise, you're going to think that you have an amazing model when really it's not. Because it's looking at future words or the word itself. So when you're trying to predict the t plus one word, you're going to be looking at the t plus one word. So you're going to think you have an amazing model. I've done that myself when trying out different things. So yeah, need the causal mask. And that's it for today.